Good morning. So we will discuss now about time harmonic fields. See, you take any physical quantity. That physical quantity, you can say that is time harmonic if that varies sinusoidally in time. Okay, that physical quantity you can take it as voltage, current, field, or anything. If that varies sinusoidally in time, you could say that is a time harmonic field. So, or a time harmonic function. So a time harmonic field is one that varies. So time harmonic fields that varies periodically or sinusoidally in time. Because so far you observed that the time dependence of electromagnetic fields has been chosen arbitrarily. So to be specific, we shall assume that the fields are time harmonic, means they are varying in time. Sinusoidally, they're varying in time. Sorry. So now the sinusoidal analysis is not only of practical value of interest, it can be extended to most waveforms by Fourier analysis. Okay, and also the sinusoids. So when you have sinusoidal variations, so you could say these sinusoids are easily expressed. They are easily expressed in phasors. Yeah, so this is a brilliant concept. So whenever I say a phasor, see, you know what? Algebra with complex numbers is easier than with sinusoids. So phasors are simply complex numbers. Yeah, in their complex numbers. In elementary language, you would say phasors are something like rotating vectors. Okay, so when sinusoids are easily expressed in the form of phasors, now using these phasors, now mathematics becomes really simple. Okay, so before applying phasors to electromagnetic fields, it is worthwhile to have a brief review of the concept of phasor. So as you know, a phasor is a complex number that contains that so that contains amplitude and phase of what? So amplitude and phase of a sinusoidal oscillation. Very important stuff is this. Okay, so therefore it is generally a complex number. So as a complex number, any phasor, okay, let me take a phasor. It's a complex number. I can take a phasor Z, and this can be represented like this: a phasor Z equal to x plus say jy in the rectangular form, or I would say this is nothing but r angle phi. This is polar form. So this stuff is polar form, and this one is rectangular form. Okay, so if you want to play with additions and subtractions among these complex numbers, then rectangular form is recommended. And if you want to just multiply and divide these complex numbers, then polar form is highly recommended. All right, so therefore generally this one I can write it down like this: z equal to r e power j phi. Okay, so and this one is, if I expand this, so you get cos phi plus j sine phi. Now we know j is square root of -1. So I just don't save it. Let me go for another slide. Okay, and x is the real part of z and y is the imaginary part of z, and r is the magnitude of z. You have r equal to this one. You can also show like this. Okay, so r is the magnitude of z. All right, and phi is the phase of z. Okay, and that is given by, so I know, see for example, I can write R is magnitude of Z, and I know Z is equal to a, of course it's a complex quantity, so x square plus y square, which are equal to this. And phi, my phi is the phase of Z, so phase of Z, so I just take now tan inverse, tan inverse y of y divided by x. Okay, now so you have everything, of course, say in polar form. That's fine. Okay, so now anyways, if you want to perform some as we said already, some algebraic stuff, that is if you want to add two complex numbers, then you go for rectangular form, or if you want to just multiply two complex numbers or divide two complex numbers, it's often good to go with polar form. For example, say I would say like this: I have two complex numbers, z1 is r1, say phi 1, and z2 is r2. The magnitude of z2 is r2, and the phase of z2 is say phi 2. So we have like this. So as you are well familiar with this, so I can multiply the magnitudes. I can, simply add the phases. Okay, and if you go for division, so z1 over z2 is simply r1 over r2. So you have this one first, so phi 1 minus phi 2. Okay, so now as you know very well, Phasor is a complex number, and algebra with complex numbers is really easier than with sinusoids, and so therefore we often go with phasors. So whenever you have sinusoids, you can express them in phasors, and we make use of mathematical convenience working with phasors than with sinusoids. So that's the main reason we are going with phasors. So you have electric and magnetic fields. Okay, so of course now in this analysis we are dealing with time harmonic electric and magnetic fields. That means electric and magnetic fields, they are varying sinusoidally in time. That's the assumption we have now. And now slowly what we do, slowly we convert this sinusoidal variation of electric and magnetic field in the form of phasors. And now we will appreciate the beauty of the simplicity of mathematics involved with phasors. So before we venture into that, so let's represent. So representation of a phasor. Okay, of a phasor, say in the rectangular form you have x plus jy, and this becomes in the polar form magnitude of z equal to r and phase of z equal to phi. So I can show this way. Okay, so this is my real stuff, a real part of z. Okay, so real part of z, say you have some x, and imaginary part of z, say you have some y somewhere here. So I have x plus jy, so I have x plus jy for some x and some y. You have this, and then we would say, this is okay, the resultant stuff. I mean the direction, you have the direction is this. So this is the direction of this. Okay, so this length of this vector is, say, I mean length of this stuff is nothing but your r, that is magnitude of z, z equal to x plus jy. And of course, by convention, anti-clockwise journey is my positive journey. So this is what the angle phi. Okay, now the rotation, the angular speed, if you want the angular speed, so this I can take as my angular speed, or in this case you have angular frequency, radians per second. Okay, so I mean you have this, I can take a z conjugation, so you would get x minus jy. So this becomes the phase. If I take x minus jy my phi would point down or it would go clockwise. So therefore I can show with that negative phase. Okay, so also I can show this one as e power negative j phi. All right, now what we do slowly to bolster our discussions, we will, and to maintain, we must be cogent with our discussions. So to maintain that, we will introduce, so we will introduce time element. Okay, let's introduce time element instead of phi, because what we have is z equal to r and phase of z is phi. So as of now, this phi is, means we just took as a phase, just like that. So now what I do slowly, this phase, I'll show it like this. We will introduce time element omega t plus, let me say theta. Of course, theta is, say this theta is in radians or degrees. So let me take this theta in radians. Now I know omega is radian per second and t is again in seconds units. So again you have radians. So radians is what is phase. So I can, of course, I can take some modification for phi like this omega t plus theta, so that I have an opportunity to introduce this time stuff, time element. So when we take time element like this, okay, now that means, otherwise you could say, now I could say this theta may be a function of time. Okay, this theta may be a function of space coordinates, like you have like xyz, whatever it is, or this theta could be a simple constant. Okay, so in this case, we are taking theta in radians form, and of course omega t is also in radians, so phi is very simple now. So therefore, what I have is, uh, z equal to, you have r phi. That means I can construct this way, r e power j phi. Now slowly we introduce the time stuff, we have an opportunity. Now phi is equal to omega t plus theta. Okay, so therefore we can write it down like this, r e power j omega t multiplied by e power j theta. Okay, so and this is represented by, so this stuff is represented by this real part of r, what you call e power j phi. Okay, I can, I mean, what we are saying is that in this case, the real part and imaginary parts of this you can take. Okay, so in the real part you will get cosine, and in the imaginary part you will get sine. So to be more specific, let me go like this. So this is e power j theta. Of course, this is what you have like g. So let me go to two parts now, real part and imaginary part of this. Okay. So what I have for this. So I'm doing everything for this, r into e power j theta equal to this, and this became this one. So finally, r into e power j phi, what you have is r e power j theta and e power j omega t. So I will try to find out the real part of this. So a real part of r e power j phi, and also I just want to find imaginary part of r e power j phi. So uh, so without a second thought, so let me put it down like this again, r into e power j phi is equal to, we just obtained r e power j theta multiplied by e power j omega t. So real part of this, so real part of this stuff is equal to what? Okay, so I can say this is because this is equal to this. So real part of this is nothing but what? R cos omega t plus theta. All right, so you have this, and imaginary part of this imaginary part of this means of course this. So you would get r sine omega t plus theta. Okay. So finally, now for example, if I introduce a physical quantity, we said, right, any physical quantity, if that varies sinusoidally in time, you take any physical quantity, if this a physical quantity, if this varies sinusoidally in time, sinusoidally in time, then we would say this physical quantity is time harmonic. Okay, this is a time harmonic quantity. So that is simple. Now physical quantity means, just don't confuse anything, because I can say current is a physical quantity, voltage is a physical quantity, okay, energy is a physical quantity, or I can say a field, electric field is a physical quantity, magnetic field is a physical quantity, temperature is a physical quantity, so on. I can take anything. So for example, if I want to choose current, okay, as a physical quantity, and I would see now that time harmonic nature for say current, now I would think like this. So I take a sinusoidal current. if if we take sinusoidal current, so say, let me say it is I of t. So now I of t is equal to, say, something like, I just take real part of this. So say you have omega t plus theta. So I of t is equal to I naught cos omega t plus theta. That means the physical quantity current is varying sinusoidally or cosinusoidally in time, and that's it. So so of course, if I take its real part, this is nothing but what I can take, like this, real part of I naught e power j theta multiplied by e power j omega t. You can also take imaginary part of this. If I take imaginary part of this, I would get I naught sine omega t plus theta. That means it's not that always you can use only real part. You can also use imaginary part. That means either you have to use real part or imaginary part, but please don't involve both in the same calculations. Okay, so that is important. That means I would say, for example, something, say some extra one, say some I prime t is equal to, also I can take the physical quantity, this current, not only cosinusoidal, also I can take this sinusoidal I naught sine omega t plus theta. Okay, so you're showing a physical quantity current again in the time harmonic form. Okay, so that means this we can eschew, like this, imaginary part of I naught e power j theta e power j omega t. And also, if you really are comfortable with cosine stuff, okay, if you just don't want to go with sine stuff, if you really want to, if you think you're comfortable with cosine stuff, then what you do, the same thing. Whatever you have for the same thing, I can write it down now with introduction of 90-degree phase difference. Okay, so that is what I can do. You can introduce a phase shift of 90, and you can make things done. For example, what I know is, generally say some sine theta is equal to, you have some cos theta minus 90 or cos 90 minus theta, because cosine is even stuff, either of the stuff is okay. So you can put it down like that. So instead of, if you don't want sine, if you want cosine, so take the argument, whatever argument you have, just add 90 to it. Okay, and so anyways, to get what you call, so that means to be consistent in our use of either the real part or the imaginary part of a quantity, then of course you must go with either a real part or imaginary part, but not the both. Okay, don't take the both at a time. Okay, so therefore, anyways, not to make things complex, the complex term, so whatever we have, the complex term I naught e power j theta. Okay, because you see, moment ago we had this, the complex term I naught e power j theta, and this resulted from dropping e power j omega t. Okay, so what did we do? We just took real part of I naught e power j theta e power j omega t, and of course you have imaginary part of I naught e power j theta e power j omega t. Just drop this stuff. If I drop this, now I'm just taking this one I naught e power j theta. Okay, and now we just dropped this. Okay, from I of t. Now this is called as Phasor current. Okay, just drop this from, for example, forget about this. Take this one, real part of I naught e power j theta e power j omega t. Just drop this e power j omega t and also drop this real part. Now you are seeing I naught e power j theta. Now this I naught e power j theta, this stuff is nothing but a phasor. So this is phasor form of the current. Now, in general case, we can understand this like this. Generally, this I naught, okay. So here you are seeing I naught as amplitude and this theta as phase of the current for now. Otherwise, I can say that this is a complex stuff. So generally, phasor is a complex stuff. Yes, sir. Of course, you're seeing a complex stuff. So therefore, you would say like this: you have real part of phasor multiplied by e to the power of j omega t. So that is what you're doing, okay? So of course, we started with this, right? The physical quantity as current. So we took something like this. Okay, we took something, I think we took, say, cos. We just started our journey like this, omega t plus theta. So real part of this one is nothing but this one, okay. So now that means generally that this is what instantaneous value, instantaneous current, at every time I can find my current. So therefore the instantaneous stuff, instantaneous stuff is given like real part of phasor multiplied by e power j omega t. So now, in this case, the phasor is the complex stuff, you know. So someone, if someone asks you find the phasor form of some given question, whatever, then just drop this real part and e power j omega t, and that's the phasor of that quantity given to you. Okay. So I mean that is and that is very important to understand. So this particular stuff is phasor form. This is Phasor form of, in this case, current. Okay, now you have both, say, magnitude as well as phase. So this guy is a complex value. So this is complex. So therefore, Phasor form, Phasor is always a complex number. So that is pretty straightforward now. Okay, so in simple language, I can show this one like this. This I of t, the instantaneous current I of t, is equal to, now I of t is nothing but this one, right? So I of t, because this is what instantaneous current. So this instantaneous current, I can show it as real part of this because both are same. So real part of, now what I have I naught e power j theta. So I know this I naught e power j theta is phasor current. So just to make a note, I will take this one as subscript. Yes, it's very common convention because phasor, all phasor forms, most of the textbooks they take. Yes, you can think of, he picked out this, yes, and put it down here. Okay, so like is, and you have e to the e power j omega t. Okay, now what is phasor form here? So this Phasor form is, so this guy is in not is not very well. So I naught e to the power of j theta. Okay, this is the Phasor form of the current, or Phasor current you would say, or you would say current Phasor. Okay, so of course I can write it down also like this, because this guy is always complex. Okay, so every time the instantaneous form is expressed in the form of Phasor form like this. So real part of Phasor multiplied by e power j omega t. Now we'll try to work with these Phasors and instantaneous forms. Okay, so and one thing you have to understand here, the phasor is a function of space or position, but not a function of time. Because why? We just omitted e power j omega t from the picture, and also real part you omitted. The remaining stuff is what the phasor, and in this phasor you don't have any. I mean, in this phasor you have only space quantities. So just write it down like this. So phasor is a function of position, okay, or space. I can say function of position, or I can take space, not time. It's very simple, right? So not time. Now let me take an example. Let me take a simple example. I'll take a vector, some vector a. So vector a is given to you as a naught cos omega t minus some, say we take something like beta x, okay, and this a is oscillating along y-axis. A is oscillating along y-axis and propagating along positive x-axis. So propagating along positive x-axis but oscillating along y-axis, or polarized in y. So that is what you can understand. Okay. So therefore, A is given like this. Now you can write. So we can write down this A. Now, now I'm taking what? Now instead of taking current, I'm taking my physical quantity as a field quantity. Okay, some field quantity is this. So I want to express this field quantity this way. I want both instantaneous and phasor combinations in one equation. So for that, what I do, I take this one as real part of A naught e power j omega t minus beta x. Of course, you have ay roof. So therefore, okay. So of course, A is equal to, you have real part of A naught. Okay. Now what do you have here? A naught e power negative j beta x multiplied by e power j omega t. Of course, you have here A by roof. Now what do you do? Okay. If you want Phasor form, just remove this guy, real part, and remove this time dependency, this e power j omega t. Now, whatever you're seeing here, this is Phasor form of this A. Okay, now you're seeing here, okay, see j beta x, x is my spatial quantity. For example, if I take electric field, dynamic fields, they are functions of space as well as time. So I say, if I say E is varying in space and time, so space variables are this xyz in Cartesian system, and of course in time I can take like this, so xyz like this. So as of now, you are seeing one variable out of three. That means you have a one-dimensional wave equation. A wave is propagating, say, along positive x-axis, okay, positive x-axis, while oscillating along y. So the wave is oscillating in y-axis, and that is what is ay, but propagating along x-axis, positive x-axis, and that's what you have, this negative beta x in this case. So anyways, so out of three we took one, so you have a one-dimensional wave, and you have to note this: waves will not travel like this in free space. You don't have any one-dimensional wave in free space, okay? So always you have three-dimensional stuff. So for simplicity point of view, we just consider one variable out of three, and that's it. This is only for mathematical convenience. You can put all three variables if you want x, y, z. So further then what you do, you have to take like this, some wave vector dot product with position vector. Okay. Now in this case you have all three components. I can take generally. Okay, where r equal to x ax roof plus y ay roof plus z az roof. Okay, so k is equal to say kx ax roof plus ky ay roof plus kz az roof. So you know all these things already we discussed in our class. So, so what I can say now? Now I can say this is my simple Phasor form. Okay, so let me take down my Phasor form is this. Now you understand, you already understood. I'm sorry. So what is, why Phasors are really useful? Because in simple words we can say the algebra with complex numbers is easier than with sinusoids. Okay, a phasor is a complex number. So when you have time harmonic fields, that means those time harmonic fields nothing but they are fields which vary sinusoidally in time. So whenever you have fields that vary sinusoidally in time, those sinusoidal variations you can approximate to phasors. So that flexibility you have, sinusoids to phasors. Now you have complex numbers with you, just play with algebra because algebra loves complex numbers, or complex numbers also loves algebra. Okay, so and anyways, we will not see now whether phasors love to work with calculus or not. That is secondary. So as of now we are very eager to find out my phasor stuff. I want to know my phasor stuff. I have vector A. Now from this I found my phasor. So phasor I give subscript yes here. Okay. So my phasor stuff is, of course, phasor could be a rotating vector. So I'll take it as a vector. So I have, just now we found a naught e power my negative j beta x. There is only spatial variation, but there is no what you called time dependence. Okay, so this is what you have. You have some propagation along positive x-axis. Okay, so now what I do, there is something interesting now. Okay, what is our a? Already we took a in the question. We had a like this. A is equal to a naught cos omega t minus beta x, and this is a y rho. This is what we considered for a. Okay. Uh, Now A is this. So now what I do is, let me, so now I can say, how do I write this? Okay. Before I make anything possible, let me make something uh, more general like this. Say this A is nothing but, I can say, real part of phasor A multiplied by what you call e to the power of j omega t. This is, of course, the most real stuff. Okay, the most real stuff is this. Okay, anyways, you can take a y roof or anything ax roof or whatever, that depends upon the question in this case. Okay, now what we do is, let us differentiate this. Okay, so let us differentiate this, or I must also, of course, construct this. So I'll make my final stuff like this. A is equal to a real part of. I'm writing the same thing. I'm just using my phasor stuff. Instead of AS, we took phasor stuff like this. And of course, you have AY roof. This AY roof is there. And of course, you have e power j omega t factor again. Okay. So real part of this is of course this guy. And that is what very obvious. Now what I do, of course, you can differentiate this. Just differentiate this with time, because of course I'm having okay time quantity here. So if I differentiate that with time, dou A by dou T. Now so dou by dou T. Now what is my A? My A is, I have real part of, okay, so real part of, I have phasor form like this. So anyways, a phasor form is also a vector, so there is no second thought. I'll give, of course, a vector here. So see, the if I don't take this guy, if I don't take this AY roof here, you have to understand that you have AS like this. All right. So this is like AS. This is only AS. That means you have AS is equal to, say, of course, say you have AS AY. Okay. So finally, you just forget about everything. So when I don't take here this unit vector, that indicates this is a vector. I can take on this is a vector now AS. So now you have AS Phasor, of course. So vector, so multiplied by e to the power of j omega t. So when you have this, now if I differentiate this, now you tell me one point. Now this EAS is a function of space because I don't have any time quantity here. I have only space quantity, spatial variable x or y or z, whatever you have to take that. So I don't have any time stuff here. So it's customary to go this way. So real part of now what I do, so I take EAS out. So this dou by dou t, I'll take it inside and I differentiate this. There's nothing to do with AS because there is no time dependent stuff in AS. So therefore, I took this dou by dou t all the way to this e power j omega t. So now what you get? So you must get a real part of, so you have AS, okay, dou by dou t is nothing but j omega e power j omega t. Okay, that means what I can say is this real part of j omega Phasor vector, okay, Phasor vector you have is and multiplied by e power j omega t, and this is what dou a by dou t. All right. So what do you mean by this? So time derivative of the instantaneous, this is my instantaneous quantity because my A is expressed in the form of sign variations or cosine variations, whatever. So this is what this complete stuff is my instantaneous stuff. So within this instantaneous stuff, you have converted something like this or this way. Both are same. Okay. Now in this form, you can see both Phasor as well as my instantaneous stuff in the left, Phasor in the right, like this. So I would say this one. The time derivative of instantaneous quantity is equivalent to multiplying its Phasor, okay, its Phasor form by j omega. So this is a very important note. Yeah. I mean, in simple words, I can do this. So whenever you have dou a by dou t, this is instantaneous stuff. So time derivative of instantaneous stuff, you can replace this by j omega Phasor stuff. Yes, that's it. Okay. So hereafter, if someone is asking you convert, for example, Maxwell's equations in Phasor form, wherever you find dou by dou t, just replace dou by dou t by j omega. So everybody says just replace dou by dou t by j omega. And why so? That's the reason we did so far. Similarly, what I can do if I take integration of a dt. Now, it's needless to say, it is very simple, okay? So Phasor form by j omega. So if you take time derivative of a, you will get j omega multiplied by as. If I take integration of instantaneous vector this a, you would get Phasor vector by j omega. Okay. So anyways, see in circuit theory, what you do, you of course you take real part of things, and you can also take, of course, imaginary part, but by convention, they'll take real part of your Phasor multiplied by e power j omega t, all those things. So one thing you have to note down again. So if I take instantaneous form, so generally I have vector A, say it is varying both space and time. And this instantaneous form, this is time dependent, of course, and of course real. Okay, this is time dependent and real. Whereas this phase, if I take Phasor form, okay, if I take this Phasor form, that means, of course, you have also space. See, if you go to circuit theory, in circuit theory, we don't have any space. For example, I say I of t. So the time as a function of, sorry, the current as a function of time we treated there. But in field theory, also we have to include space. For example, say x comma t. This indicates current is traveling along traveling along positive x-axis. That means current not only varying in time but also varying in space. So that's what we take in field theory. We could say circuit theory is subset of field theory. Okay. So generally, whenever you say instantaneous form, say if it is in field, if it is in field theory, the instantaneous form is of course a function of time as well as space. Okay. So of course it's a time dependent instantaneous form. But if I take this, what you call the Phasor form, in Phasor form, we omit the time. There is only space. It's only space dependent. All right. So this is of course time dependent, but this is what spatial dependent I can say. So that's what we can construct, or we can conclude something from this. Sorry. Okay. And also it is easier to work with this Phasor form, as we know, and you can obtain this instantaneous form A from AS very easily. Okay. I can put it down like this. Okay. So I can obtain A from AS is easy. I'm really happy with this. Okay. And now, so what I do, slowly we will creep on to Maxwell's equations and we will see their Phasor forms now. Okay. So, sorry, I have little throat pain. I need to take some water in the middle. I'm just doing that. So now it's time to understand Maxwell's equations. Maxwell's equations in Phasor form. Okay. So for example, what you have, I have curl of Faraday's law, Michael Faraday's law. So I have minus dou B by dou T. All right. So now to be more specific, let me include all the space and time quantities. So I'll take my E like this. E is depending both in space as well as time. So curl of E is nothing but minus dou by dou T. Now I take B also is a function of both space and time. Okay. Now, see, this is what in the instantaneous form, you have something in the instantaneous form. So you convert this to the general form where also we can include Phasor stuff, that is E, X, Y, Z, T is equal to, I can take down real part of, okay, Phasor. So now you will never confuse, right? So this is my Phasor. So Phasor form is only space dependent, okay, not time dependent. So therefore I can omit T there. But in the reality, of course, I have this T. Now this T, in this case, of course, my electric field is sinusoidally varying in time. So with that clarity, we will introduce this guy e power j omega t, because real part of this, you can make this one as this. And this is very simple, okay? Instantaneous form is real part of Phasor form multiplied by e power j omega. And this is what a time harmonic nature. This time harmonic indicates that the field is sinusoidally varying in time. That's it. So I keep repeat this every time because students often struggle understanding time harmonic nature. So similarly, I can write down my B. So B x y z t is equal to real part of Phasor form of my B. The sky is of course space dependent xyz, and let me include time harmonic nature, that is e power j omega t. Okay, now what you do, just use these two. So just use these two in this equation. So that means let me what I do, let me copy this now. So I just copied that, and we would now, what equation you have for Faraday's law? You have curl of E is equal to this. Now plug in that stuff. So you have curl of, okay. So instead of E, now what do you take? I take this one, real part, okay. Now I'll take like this. I'll use square brackets here. So let me take real part of Phasor form of instantaneous. This E is Phasor form. Here we are taking ES. I can take in brackets XYZ, but for simplicity I'll omit that ES. Okay, and also I have e power j omega t, because we know ES is function of space, not time. So that part we know. So just omit that only for simplicity point of view. Okay, otherwise you don't require to omit that. Okay, so curl of E is this, is equal to, now what you have, minus dou by dou t. So I take now B, this instantaneous B, we will take it in the combination of both Phasor and time harmonic stuff. So Phasor form of B is this, so B is e power j omega t. All right, now you tell me, can I say, can I take what you called uh, can I say that this curl operates only on space, or this nubula, whatever nubula you have, this nubula operates only on space, not on time? Why? Because this nubula, or what you call delta, this is simply a nubula. This nubula is a vector differential operator. So nubula, if you take Cartesian system, it is a vector differential operator. You know very well, that means nubula by itself has no significance, but when you operate this nubula on a scalar or a vector, then you can construct, then you can extract the significance of that something because of this nubula. Okay, so dou by dou z is a roof. This is what nubula, that means this nubula operates spatially. There is no time stuff here on the right hand side. So this ES is talking, this ES is spatial dependent stuff, and you have e power j omega t. So there is nothing to do with this, yes or not? So therefore, now what I do, um, now what I can do is this. I can say curl of, now curl of, I can say, how can I put this in simple words? Let me directly write down this one like this. So this one, let me try to put in simple words. Okay, so I know this curl is nothing to do with this time stuff, because it is a spatial variation stuff is that. So this ES is spatial dependent stuff. So therefore, let me bring this nubula inside the square bracket. So now you have real part. Okay, try to understand this, it's very simple, there's no big deal in that. So you have something like real part of curl of ES. Okay, so real part of curl of ES, now it is multiplied by e power j omega t. So this clarity you must have. Okay, so once you have this clarity, then things will work out for us very well. Okay, so this one is this. Now what about this one? So this one, how can we write? So again, now this BS is spatial dependent, but this dou by dou t, something is varying with time, okay? So I want something, a variation in time. So there is nothing to do with this dou by dou t and BS. So therefore, what do I do? The real part of this. So I'll take this dou by dou t inside. Let me bring it here, dou by dou t, e to the power of j omega t. Of course, you have negative sign here, so I'll take that negative sign. Okay, this negative sign I have here. Now, what do I get? So if I solve it further, this is nothing but negative real part. Okay, so what is dou by dou t of e power j omega t? So this is j omega multiplied by e power j omega t. So this j omega, I'll bring it here, and you have Phasor, okay, BS, and of course you have your e power j omega t. All right. So now what do I do? Now I can say that means what do I do now? That means this quantity, I mean this quantity is equal to this quantity. So therefore, uh, now what do I do is this. So I say that on the left hand side I have a real part of this is what we brought inside curl of Phasor form. So curl of ES e power j omega t, and on the right hand side we have minus real part. Okay, so we just found this j omega multiplied by Phasor Bs e power j omega t. Now you tell me there is, now once you simplify this stuff, there is nothing to do with e power j omega t. So just cancel out this e power j omega t. And do you want to do anything with this real part? Yeah, so there is nothing to do with this real stuff as well. So let me rule out this real stuff as well. Now what are you seeing here? So you are seeing simply curl of ES is equal to minus j omega PS. So this is what Maxwell equation, okay, Faraday's law in Phasor form. So we simply uh, uh, treat directly with, that means you have curl of E is equal to minus dou B by dou T, and people write it down in the Phasor form like this. Wherever you have dou by dou T, they replace dou by dou T by j omega and they say. So if you want to digest everything, so this is what the proof we just have now. Okay. So whatever, simply we can say. So this is the Phasor form of this equation. Okay. So Phasor form of this equation is this. All right. So this is again a very important stuff to understand. Like that, you can also you can also go with the other terms, like you have curl of H. So what is your curl of H here? Modified Ampere's law. Curl of H is equal to, you have JC plus JD, where JD is displacement current density and this is conduction current density. So according to Ohm's law, JC is equal to sigma E. So now if you want this in Phasor form, I want to uh, convert that in the Phasor form. So now what you get on expectations, of course. So I have, because my H is dependent both in space and time, but curl is dependent only on space, not on time, that e power j omega t, I can factor it out. So I can say like usual, curl of H's Phasor form of that instant. This is instantaneous form. This is Phasor form. So curl of Hs is equal to, okay, so this is conduction current density, Jc, plus what you do here, dou by dou t, it's nothing but now j omega. Now Now I take Phasor Form. Okay, and that is what you have. So it's very simple. So hereafter, I hope you don't have any confusion with this Phasor form and instantaneous form. Now I hope you can solve any problem, okay? We can solve directly. So just like that, you can solve the problem. So this, I just want to make very clear. So we will assume time factor, okay? So if you assume the time factor for to maintain harmonic nature. So if you assume time factor e power j omega, I can also assume e power negative j omega t. So I'll assume time factor e power j omega t. And the time harmonic, the time harmonic Maxwell's equations, the time harmonic Maxwell's equations say both in point form and integral form we will see, and we'll wind up this session for now. Okay, after this we'll wind up, not now, just it takes some 3 minutes to 5 minutes. So point form, and let me take integral form of Maxwell's equations. Okay, so yeah, so what is my point form here? The first one is Gauss's law in electrostatics. Okay, Gauss's law with electric fields. So Gauss's law with electric fields, which color I can take? Let me take this color, right? So I know divergence of D in presence of source. I know divergence of D. Divergence of D is equal to what? Generally, rho V, we say volume charge density. So we will take Phasor form, okay? So divergence of ds, that means we have only space. See, even this charge density is also a function of space and of course time in general case. So therefore, I see in Phasor form, I don't have any time dependence. So therefore, we will take rho Vs, okay? So yes, we took as capital. So this is Phasor form of volume charge density. So it's corresponding, we will use white, it's corresponding, okay, so divergence of D, upon divergence theorem, have to take closed surface integral. So Phasor form ds, because this is something to do with space. So the area also we have in space, not in time. So therefore d dot ds is equal to this one. Of course, I think you know all these things. So we have done everything in class about this divergence theorem, all this integral forms, everything. Just relate with that. So you have dou v for dv, differential volume is this, or elemental volume you could say. And again, second one, what do you have here? I have divergence of p. I take divergence of Phasor form. It is always equal to 0. What's the meaning of this? There is no magnetic charge, or we could say there is no magnetic monopole. Okay, so leaving flux is equal to entry flux. That means there is no starting or ending point for a magnetic lines of force. So anyways, in simple words, we could say we have electric charge. So therefore, when there is electric charge, say a density, of course, you have divergence of P. But there is no magnetic charge. Magnetic charge is possible mathematically. Hypothetically or mathematically, it is true. But physically, in this universe, as of now, there is no magnetic charge. Okay, so therefore divergence of B is always equal to 0. Whether it is statics or dynamics doesn't matter. So therefore, I have divergence means I have to again apply divergence theorem. So I must take closed surface. So Bs dot ds is 0, and colors are not good, but please accept for now. Okay. So I have curl of es, I take in Phasor form. So this is nothing but negative j omega. So Bs. Okay, if you want in the integral in integral form, Now I can apply, for example, I have Stokes theorem, right? You already know this Stokes theorem. So for example, you have something like E dot dl. This is closed line. This corresponds to what? Open surface E dot ds. This is what Stokes theorem. Okay. Anyways, so I use that. It is curl of E. So I use that. So this is now es dot dl is equal to minus j omega. So what do I do now? I can take bs dot ds. That is here. Okay. So this is, of course, we have done this. You know this very easy. And last one, none of the colors are good, I think, except white. Okay. So in the point form means you can say differential form. So curl of Hs. Okay. This is nothing but conduction current density, Jc, plus j omega. I mean, dou d by dou t. Dou by dou t, I can take it as j omega in Phasor form. So dou d, d also take in Phasor form, ds. So you have Phasor form for the, I mean, point form. Now you have on the right hand side, you have, whenever you have this curl, what I'm doing here. hmm, Okay, see, according to Stokes, see this says that closed line corresponds to, so closed line corresponds to open surface. That's true. And according to divergence theorem, what you have, closed surface corresponds to volume integration. Okay. So anyways, so I'll just take this one as, so hs dot dl. So whenever I have this curl of h, I can take it as hs dot dl in integral form. Okay, so whenever you see curl of something in integral form, you take just closed line integration. This is closed line integration along this dl. Okay, for example, I take a surface. This is my surface. Say it is my open surface like this. Open surface. Now you are moving along this. No? So this, you would say, okay, this is the edges. These are the edges like on the edge of the surface. So you're moving something like this, dl. Okay, this is like closed line. This is like closed line, and this forms the surface area. Surface, yeah, and this is a closed line. The border, whatever you're seeing, that's a closed line. Okay. So of course, so you have hs dot dl is equal to, you have integral. So yeah, closed line corresponds to what? Open surface. So this is jc plus, I have j omega ds, and this is with ds, because this is open surface, right? So you have a spatial stuff here, dot product with elemental surface ds. Okay, this is also again spatial stuff. So that is what you have time harmonic Maxwell's equations. We assume time factor as e power j omega t. You assume, if you want, you can also assume time factor e power negative j omega t. That means wherever you have j, just replace j by negative j and just modify this. Okay, that means wherever you have j, just replace j by negative j in the equations for e power, I mean, other time factor e power negative j omega t. So anyways, this is the end of the lecture. So I hope you understood everything about the time harmonic stuff, time harmonic fields, or time harmonic function. Okay, you can take function, could be a function as a physical quantity. Now the physical quantity could be anything like current, voltage, fields, whatever. Okay, time, I mean temperature, whatever it is. They are physical quantities. I mean, if that physical quantity is, if you say that physical quantity is a time harmonic function, now that physical quantity is varying sinusoidally in time. So when you have that flexibility, sinusoidal variation in time flexibility, you can approximate that in the form of phasors, where phasor will contain the information about amplitude and phase of the the sinusoidal oscillations. So when you put amplitude and phase means in one form, and that form is a polar form, or simply whenever you have polar form, you can say and that something is complex. So Phasor form is complex. Now, mathematics is quite friendly, really friendly with the Phasor forms than this sine or cosineable forms. So, as you know very well, so this algebra with complex numbers is easier than with the sinusoids. So we really encourage Phasor forms to incarnate in the analysis. Okay, so it's yeah, so therefore we have to understand, because we are dealing with time harmonic fields now, so we have to understand how to modify Maxwell's equations, or how to represent Maxwell's equations in the Phasor form. And also we understood that this instantaneous form is of course time dependent, and of course in field theory also, in the instantaneous form also, you have space, like of course you have also space information. But when you go to Phasor form, I mean this Phasor form, there is no time dependency in the Phasor form. Phasor form is spatial dependent always. So therefore, you have to we can segregate things in the form of instantaneous and Phasor form. So once you have Phasor form for electric and magnetic fields, now you can operate things with algebra more conveniently. Okay, so that's the intention, or that's the motivation behind converting something to Phasor forms. Or something is what time harmonic stuff to Phasor forms. Okay, for ease of mathematics. Thank you very much for your patience, and I will forward the problems. Okay, I'll upload the problems on this Phasor form and all these things. And as I promised you already, so my next video will be on pointing theorem, and also we will solve problems in pointing theorem. So this pointing theorem will come to know that talks about conservation of power equation. So we will understand that, and there you will understand we need some constant power. When I say constant power, that is in time, not in space. We need some constant power, but not instantaneous power, because we don't require anything like instantaneous power, because the net power within that instantaneous nature is nothing, zero. So all the way we discuss is um, about average power. So therefore we will see about the difference between average and instantaneous stuff, and why we neglect instantaneous, or why we consider only average stuff, and we calculate that. So you have integration of some flux density, so that we will see of course later. So I'll not try to make things complex at this juncture. So I'm signing off now. So thank you very much for your patience. So enjoy your rest of the day. Thank you. Okay.